All right, so I really only got a couple ideas left to share with you. All right, the first one here is we're now looking at three planes. Okay, now there's a whole bunch of different possibilities that what could happen with three planes, but the main ones we're looking at is where all three of them are coincident at some place. Now, what you could have is you could have three planes, and I don't know if I can even draw this. You've got one plane this way, one plane that way, and then you've got a third plane that somehow crosses through maybe in this way, which then allows them to all cross at a single point. Okay, so that's one possibility, is that all three of them cross at one place. Another possibility is that they all cross kind of looking at it from maybe a side perspective, that we've got one there, you've got one here going back behind, and then the third one maybe is going through in that direction, so that they all actually cross right here along a single line. Now, other than that, you can have two crossing in one place, two crossing in another place, and you could have parallel and all these other things, but really none of those are important because none of those have solutions to this specific situation. All right, so let's go ahead and look at this and see if we can figure out how to deal with it. Okay, so first thing we're going to do is we're going to go ahead and try to solve this system, because if we can solve where they're all equal to each other, then we know where they meet. So I'm actually going to take the first two, and I'm going to try to eliminate one of the variables here. All right, so let's say maybe that we want to try to eliminate the z. So I'm going to take 7x plus 4y plus 5z, and the top equation then I'm going to multiply by -5, so it'll be negative 15x minus 10y minus 5z equals -5, whereas this is equal to 3. And if I put those first two equations together, then I get negative 8x minus 6y equals -2. Then we're going to do the same thing with maybe the first and third equations. So again, I'm going to try to get rid of the z there, so I'm going to multiply. So I'm going to go multiply by -3, so I'll have negative 9x minus 6y minus 3z equals -3, which will be combined with the 5x plus 3y plus 3z equals 2, and that will give me negative 4x minus 3y equals -1. And so now I have two equations with just x and y, and so using those, maybe I'll take this one and multiply it by -2, which will give me an 8x plus 6y plus 2. And you'll notice here what happens is that they both actually eliminate. And so what that means is that I now have a situation like this where they actually cross along a line. Okay? So since I've determined that because of this thing canceling out that they actually cross along a line, then the way that we go ahead to find the intersection is by doing this. We just label one of the variables as lambda. So let's just say we say that x is lambda. Okay, so then I can put lambda in for x in one of these equations, and I should be able to then solve for y. So if I make this -4 lambda minus 3y equals -1, then I can add the 4 lambda both sides and then divide by 3. So that means that y would be equal to -1 plus 4 lambda all over -3. Or in other words, y equals 1/3 minus 4 over 3 lambda, and that's fine. And then now with that, I should be able to then solve for z by plugging these two into one of my other equations. Doesn't matter which one, but it looks like maybe this one would be the easiest, so I'll just go 3 times x plus, or actually, you know what, I'm going to do this one down here because then I can multiply it by 3. So I'm going to have 5 times x, which would be lambda, plus 3 times y, which is 1/3 minus 4/3 lambda, plus 3z equals 2. I can simplify just by going 5 lambda equals 1 minus 4, 5 lambda plus 1 minus 4 lambda plus 3z equals 2. Move everything over. So I'm going to have 3z equals 2 minus 1, so 1 minus lambda, right, because 5 lambda minus 4 lambda would be 1. Move it to the other side, and then divide by 3, so z equals 1/3 minus 1 over 3 lambda. And so we go 1/3 minus 1 over 3 lambda. And that then allows me to write a equation for this line, because r is going to be equal to 0, 1/3, 1/3, plus, and then your lambda is going to be 1, negative 4/3, negative 1/3, and then lambda. And so then I have an equation for the line where these two are crossing. I've been able to write it in the parametric form just by making one of the variables lambda. Okay, now if you actually were able to solve this and you ended up getting a value for x or for y, then you would know that it actually had a single intersection point. Okay, if you went through this and at some point you ended up getting something like this, well, you've seen that before, and that means that it's a null set, or in other words, that there is no solution to that problem. Okay, now I know this was some weird mathematics, but hopefully the idea behind it kind of makes sense, that we're solving when we get to a certain point. If we find an answer, then great, we got an answer, we got an intersection. If something cancels out such that two of the pieces are identical, negative 8x minus 6y equals negative 2 and negative 4x minus 3y equals negative 1, then all you have to do, that means that it's a line intersection, and so you make one of the variables lambda, plug it in, solve for the other two variables, and then you can write an equation. Now note that this one right here, you could very easily multiply everything by 3. Right? Or you could multiply by something which would then make these so that they weren't fractions. And there's nothing wrong with that. That you can do that and it'll give you a vector, because all, multiplying by a scalar only changes the magnitude. It doesn't change the direction. And so very easily you could rewrite this in some different format that didn't have the fractions if you felt that that needed to happen. Okay? So let's go ahead and we'll do our last little thing here, and hopefully we can do it in just a couple of minutes so that we can finish off in this last video. So the last thing that I want to talk about is the distance from a point to a plane. Okay, so let's say that we've got a plane here and there's some point, and I want to know how far is that point from the plane. Well, generally speaking, okay, not generally, all the time, when we talk about the difference from a point to a plane, we're talking about the shortest distance, which the shortest distance has to be perpendicular to the plane, because any other distance, if you drew a triangle, any other distance that you went would be a hypotenuse relative to that normal, and so therefore any other distance, no matter where you went, is longer. The shortest distance is perpendicular to the plane. Now what that does is that means that we're actually going to be dealing with a normal vector, right? A vector that's normal to the plane. So if you want to find the distance of a point from the plane, the first thing you need to do is write the equation for the normal vector that's going through that point. Then what you do is you find the intersection of that line with the plane, and then you can find the distance. Okay? So what we're going to do is we're going to go ahead and actually try that. Let's say that we have a point, A, 2, negative 1, 3, and then we have a plane, x minus y plus 2z equals 27. So here's my plane, here's my point. So the first thing I need to do is I need to find the normal to the plane. Normal's easy, right? Normal is just 1, negative 1, 2. It's a good thing we figured that out earlier, because now we know we can just take the coefficients, and that's the normal vector. Now that's just the direction of the normal vector. So what I need is I actually need a line that's going through the normal vector, that is going in the direction of the normal vector and going through that point. And so that also is easy given what we already know, because we need a starting point 2, negative 1, 3. And then I need to make sure that I'm going in the proper direction. 1, negative 1, 2, with some parameter, which I'll continue to use lambda, so I'm being consistent. So now I have a vector that's going through this point perpendicular to the plane. And so now, if I want to be able to know the distance, I need to know this point right here. So I need to find the point of intersection. Now, we've done that before, right? We found the point of intersection. And how did we do that? Well, we took this line and we wrote it as parameters. We said x equals 2 plus lambda. We said y equals negative 1 minus lambda. And we said z was 3 plus 2 lambda. And then we put all those straight into our equation. And so we put that into the equation for the plane. And we go 2 plus lambda minus negative 1 minus lambda. And then plus 2 times 3 plus 2 lambda. And that all equals 27. And so we've got 2 plus lambda plus 1 plus lambda plus 6 plus 4 lambda. Man, this is fun. And then we can put these numbers together. 2 plus 1 is 3 plus 6 is 9. Lambda plus lambda is 2 lambda, so we got 6 lambda there. Subtract the 9. So we got 6 lambda equals 18. Divide by 6. We got lambda equals 3. There we go. We got lambda. We put it back in. And we get 2 plus 3 is 5. We get negative 1 minus 3, which is negative 4. And we get 3 plus 2 times 3, which would be 8. And so now I have the point where it crosses. And so now that I know the point where it crosses, 5, negative 4, 8, we can find the distance to the plane because we know where A is, we know where it intersects, and therefore we can find the distance. So we'll go square root of x minus x squared. So 2 minus 5 is negative 3. Squared is 9. Plus negative 1 minus negative 4, which would be 3 squared. That'll be 9. And 3 minus 8. 3 minus 8 is negative 5. Squared is 25. And we put all that together to get the magnitude. We got 18 plus 25, which is 43. And so therefore the distance from A to the plane is the square root of 43. As far as I'm concerned, that is some cool stuff. And this question right here was able to take a lot of the things that we've learned, the vector equations, the points, the intersections, the finding a normal, all that stuff, put it together into one problem. Great problem, gives us a distance, and we're now good to go. You are done.